I'm very excited to be back in Barcelona, my first trip back here since the pandemic, and I've had a chance to reconnect with some local Barcelona folks, which is very exciting as well. I'm Stan Farnsworth, Chief Marketing Officer and founding member of PulseForge, and also the elected chairperson of the OEA, which is the largest international association for printed and flexible electronics. And this is a concept vehicle that represents a convergence. This is a convergence of a variety of technical topics. It's a convergence of a variety of aesthetic topics, and it's a convergence of a variety of environmental topics. And unfortunately, our technologies right now, it also represents a convergence of some negative pieces as well. So it turns out that thermal processing is one of the largest contributors to global greenhouse gases. And when we think about even outside of concrete and steel, just general thermal processing for manufacturing, depending on which numbers you look at, are in the 10 to 30% of the total greenhouse gas contribution. And so at PulseForge, we're taking all of these pieces into account. And the challenge is that we need to get to this kind of aspirational product. And from an electronics perspective, we're almost there, but we're not quite there yet, because this represents 40 years of evolution of electronics. And the cell phone is a great example for this. It's a tremendously capable device, but we can see it's gone from this kind of structure, and I see a few folks here that probably had one of these. I had one of these, but all of us have one that looks like this. And that's because this kind of device is based on technologies that look like this. And that's okay. We spent a lot of time developing and understanding the technologies that go into this. But the problem is that this kind of technology is a brick. And this doesn't look like a brick, and I don't look like a brick, and I don't see anybody in here that looks like a brick. So we have to figure out how to get from this kind of technology, which is where we are, to this kind of capability, which is an aspirational capability. And at PulseForge, we've done this by putting a team together to think about technology and power from a variety of very different physics and science and engineering perspectives. And so our team has folks from nuclear power, plasma fusion. We heard a little bit about fusion today already this morning. Railguns, which is a really interesting topic when we want to talk about really intense delivery of pulsed power, which is very relevant. Light. This is a representative laser light. We wind up using light energy as our energy delivery vehicle, but also including semiconductor, reentry vehicles. This is another personal favorite of mine, going back to our origin days, almost 20 years ago as a nanomaterials company. And so we're looking at a combination of material science and a combination of really extreme levels and forms of energy and power. And this is a very classic deep tech exercise. And this is how we get to go from something that looks like this to something that gets more of an aspirational product for us. And so when we take this kind of approach, we wind up building a tool like this. So this is a production manufacturing tool that PulseForge has built and released this past year that is literally the result of 20 years of understanding how to use light energy to harness that to do real manufacturing work from a very different perspective of delivered energy. And so this kind of product lets us do things like this. So we can instantaneously solder on low temperature substrates. This is a large area process. This is not a laser doing point to point to point. We can process and build electronics on curved, fully three-dimensional surfaces. We can also look at doing different kinds of connectors, so we can directly connect components to boards. We don't have to work with connector pieces, which adds complexity. And this is also one that's really interesting. These are coin cell batteries soldered directly onto a piece of plastic. Now, I'm not necessarily recommending that we solder coin cell batteries onto plastic, but this does represent an ability to look at novel forms of battery technologies that are very sustainable, that do not hurt the environment, and this comes back to our convergence point of how do we get past the negatives in the technologies that we're adopting to build aspirational products. So for this kind of technology, our soldering works very well. So we can use this electronics manufacturing capability to still do this kind of technology. That's okay. I'm not technology shaming anybody. This is still a really important part of how we do things. And in fact, the concept of flexible hybrid electronics is exactly predicated on taking advantage of the technologies that the last 40 to 50 years have developed and refined and are continuing to move forward. And in fact, the panel discussion we heard just now was really interesting because this is talking about how do we take lessons that we've learned and apply that to new technologies. But we can also do things like this. So these are LEDs that have been soldered onto a piece of plastic. And it's a regular manufacturing process, but it's on low temperature plastic. And so this plastic is exactly the kind of plastic that we'd use on a water bottle. It has a melting temperature of around 150 degrees. Regular conventional solder has a melting temperature of about 260 degrees, but it's well established and well used in manufacturing. And so we can do things like this, which is directly solder the components onto this plastic. And it seems like it should be completely impossible because the melting points are so disparate. But with our processing technology and our novel use of energy, we're able to overcome these kind of gaps. And this is what happens when you take a novel technology and approach some kind of problem with it. It's that it takes what seems like an impossible solution, but because we're coming at this from a different set of technology attributes, and we're looking at different sets of properties, then the impossible becomes the impossible. And so electrons are not passe. We still need electrons. We love electrons. But we need to think about doing technology differently so that we can migrate away from bricks to morphologies and products that are aspirational and get to where we want. So there are some other benefits, though, of this kind of technology. So 100 times faster production for this kind of technology set. It's a much, much smaller manufacturing footprint because we're utilizing energy much more effectively. And this is really where we get back to trying to do our best to fix the ugly picture of that convergence, which is using much less energy to do the same kind of work. So this is with our electronics today. But we're also working with designers and other influential thought leaders to think about broader implications. What are the implications of this kind of thermal processing technology on product design, product manufacturing, taking into account that we can use new kinds of materials, so not just plastic materials here, but potentially also biological materials and tissues, because we can do high temperature processing on low temperature materials. So this really opens the door for really creative thinking about materials use. We can reduce weight, so we can get AR, VR goggles that are much less cumbersome and really open the door for that. And in fact, this touches on two of our major markets for this right now. We are right now selling these tools to companies that are producing the next generation of medical test strips, AR, VR goggles, and we're using these and working with our customers to remove design constraints. And so that's what we're doing at PulseForge. And how do we get to these kinds of products and these kinds of products, and even looking into space, to an aspirational circumstance beyond where we think today, beyond our encumbrances today, to build a new reality based on new technologies. Thank you very much.